Okay, so that was a little bit of using ease 101. You can see that what we've decided then is that our chip temperature is 68.5 degrees Celsius, which seems nice and cool, so I'm not too worried. We'll come back to whether I should be worried or not, but at this point at least it looks like nothing's going to overheat. Probably, as I've said a few times, the really important thing is looking at the values of these resistances. So there's 6 of them, and deciding based on these values what should I really be concerned with and maybe what shouldn't I be concerned with. So I put each of these values onto onto this resistance diagram. So same resistance diagram, I just now have values, right? And if I look at these values, I should be able to decide what's important and what's not. And it may take a little bit of thinking about, but let's try to do this, right? So if I look at these two resistances over here, I have convection at 270 in parallel with radiation, and that's a much bigger value, 1760 K per watt. So if I think about the energy that's trying to move this direction from left to right, most of it's going to want to go through the convection resistance. Almost none of it's going to want to go through the radiation resistance. And so right away, I know that, let's see if I can be really clever here and do this. Right away, I know that this resistance here, not very important. This resistance here, at least in terms of this path, is very important, right? And actually, the other way you can see that is if you calculate the parallel combination of this guy and this guy, what you're going to find is that it's very close to 270, right? It's just a little bit smaller than 270. And again, that's because this is the important resistance associated with this path, right? So this path has a total resistance of 270. Let's keep that in mind. It's a little less than 270, but something like 270. Now let's come over and look at this path over here. All right. So here we have 4 resistances that are added together. They're in series. We said, I think last time, that when you have resistors in series, it's always the big ones that matter, right? Over here, in resistors in parallel, the small ones matter. Over here, resistors in series, the big ones matter. So right away, I know that the conduction resistance of the spreader and the conduction resistance of the chip is, neither one of those are very important. The 2 resistances that are important are actually the convection resistance to the water and then the conduction resistance across that thin but not very conductive dielectric layer, right? So this path has a total resistance of 5 plus 4, something like 9, right? 9. So I've gotten rid of 3 resistances, 3 physical phenomena that just aren't very important. So that's progress. I'm left with 3 phenomena that may be important, right? I have convection to the water, conduction to the dielectric, and then convection with the air. But actually, if you think about this guy here isn't important either. And the reason is because when I have energy coming in here at this node and I give it a choice, go left, go right, if this path is 270 Kelvin per watt and this path is 9, which direction is it going to choose? It's pretty much all going to choose to go this way, and very little is going to go this way. So this guy actually isn't very important either. And I'm left with only 2 things that are really important in terms of my thermal management system. If I want to make my thermal management system better, I really need to focus on improving the convection resistance down here, right? So maybe I want to add fins or something like that, and improving the conduction resistance here, which means maybe I'd like to learn how to make this dielectric layer a little thinner or a little more conductive. And it's not coincidental that if you go look in the journals about thermal management systems, many of the papers are in those 2 areas. Could we come up with better dielectrics that are more conductive, more thermally conductive? Could we come up with better convection fin designs that give you higher heat transfer coefficient, more surface area for less pressure drop, right? So it's tackling what's important. It's not tackling things that are not important in here. All right, so that was useful and interesting. I guess the last thing I'd like to talk a little bit about before we leave this example alone is how accurate this estimate is right here. So 68.5 degrees Celsius, I mean, I'm pretty happy with that. It sounds pretty good to me. It sounds like I'm not going to overheat anything. But if you think about it, that's not completely accurate, right? I've made some assumptions when I built this model being this resistance model, of the situation, right? So what assumption did I make that is actually limiting the accuracy pretty seriously? And let's think about that for a second. When I have energy going from this relatively small area, so here I have 1 centimeter by 1 centimeter, and I'm letting it expand into this large area, so 2 centimeters by 2 centimeters, what was my model for that process? My model for that process is that the energy could go from this small area to this large area without any spreading penalty at all, right? It could literally instantly, as soon as it got to this point, somehow magically expand or travel over to this edge and take advantage of this entire area without any additional resistance associated with the fact that, the energy actually has to move. It has to go, well, let's see, about a half a centimeter, right, to get from here to here. And I didn't penalize the process for that additional path. I have no additional spreading resistance in my model. This is actually a two-dimensional problem, right? But I'm modeling it using a bunch of one-dimensional resistors. And the way that I got by with doing that is I said, I'm just going to ignore any spreading resistance. I'm going to assume that this expansion can happen without any penalty at all. And sometimes that's called the isothermal limit, right? I am assuming that, as I move along this path, I'm isothermal all the time at any spot, right? That's the isothermal limit. And what kind of estimate is that going to give me for the resistance? Is that going to give me an upper bound or a lower bound on the actual resistance that separates this chip from the water down here? I think that by ignoring this spreading resistance, what I'm going to get is a lower bound on the actual resistance that separates this point here from this point here. I'm going to get a lower bound on the actual resistance that separates the chip from the water, which we know is the most important part of this problem, right? These resistors right here. And so that's going to give me then a lower bound on the temperature rise of the chip, right? If I have a lower bound on the resistance, I'm going to get a lower bound on this temperature rise. I'm causing this 5 watts to flow through the smallest possible resistance. The resistance is actually going to be higher. This chip temperature is actually going to be higher than what I talked about, than what I calculated right here. And so, that's important to know. Yeah, 68.5 is fine, but this isn't the actual temperature. This is a lower bound on the actual temperature. So what would be really cool is if I could also come up with an upper bound, right? If I could come up with a lower bound and an upper bound, and I was happy with all the temperatures between them, then I'm done, right? I don't have to go develop an actual two-dimensional or three-dimensional model of this situation. I'm pretty happy with this relatively simple one-dimensional model. So that is what's called the adiabatic limit, right? So here, the isothermal limit says if I have area, I can take advantage of it, no problem. No problem for me to spread out and take advantage of all of the cross-sectional area available for conduction, right? The adiabatic limit says the opposite thing. It says I'm not going to let you take advantage of any additional area, right? You start with some area, that's all the area you have the whole time. You will not be allowed to spread laterally to take advantage of any additional area along the path, right? So that's the adiabatic limit. And that's basically represented here, right? When I get to this larger area region here, I don't get to move out here and take advantage of this 2 centimeter by 2 centimeter spot. I am stuck with a 1 centimeter by 1 centimeter cross-sectional area, right? Clearly that is the highest possible resistance, right? Because here, I'm not allowing any spreading to happen. So I'm forcing myself to use the smallest possible amount of area. The true answer lies between those extremes, right? So I at least will have a bound of what my true answer is. So how does this change? How does this resistance network change if I decide to do this again using the adiabatic limit? So let's see. Nothing changes over here. Over here isn't very important anyway. In terms of going from the chip down to the water, I start with this 1 centimeter by 1 centimeter area. So when I'm going through the chip, that doesn't change. When I go through the dielectric, that doesn't change. But here when I hit the spreader, now all of a sudden I don't get to use 2 centimeters by 2 centimeters. When I'm calculating the conduction resistance of the spreader, I have to stay inside of that 1 centimeter by 1 centimeter area. So this is WC squared. Now, same thing for the water. If you want to be strict about this, down here, I don't get to use all of this area. I only get to use 1 centimeter squared of that area, right? So that is my upper bound. This is an upper bound on the resistance. So if I go back to my ease model, which I'm going to do here, let's get rid of this. And then let's come down here and do exactly the same thing, but now we'll call it the adiabatic model, right? So all the stuff is the same except that I am changing how I calculate these two resistances right here, right? Up here I had WS squared and WS squared. Here I have WC squared and WC squared, right? So now when I calculate a chip temperature, what I should find is that it's kind of a lot higher than 68.5 degrees Celsius, right? And that's because the resistance went up. So here's my adiabatic temperature, 141 degrees Celsius, right? So, that's quite a bit higher, 141 degrees Celsius. And what I've learned from this is a couple things. First of all, I've still learned what's important and what's not, right? I've learned that if I want to tackle this, I really need to think about the dielectric. I need to think about this convection. So what's important and what's not. The other thing I've learned is that this is the absolute bounding limits of what the temperature can be, right? Without doing any kind of finite element model or anything that would take a day or 2 days to put together, I have found that my chip temperature has to be between 68.5 and 141 degrees Celsius. And if all of these temperatures are okay, I'm done. I don't have to worry about it anymore, right? I could actually do a little better than that by figuring out approximately how much resistance is associated with spreading, right? So what is that thermal resistance? If I compare that value to some of the other values, I can decide, am I closer to 68.5 or would I be closer to 141 degrees Celsius, right? So that's sort of one step farther that you can go. All right, so that is resistances and resistance approximations. I guess what I'd like to do next is one more sort of resistance approximation problem in order to introduce not only this isothermal and the adiabatic limits, which are themselves useful, but also what are called the average area and the average length models, which are sometimes used, right? So we'll do that next.